In this video, I will show you how to use Maxima, and in particular a package that is built in Maxima called ctensor, in order to do computations of the affine connection and the curvature tensors of a metric that you wish to study. Please read the ctensor documentation, and there is also a preprint that has all the mathematical details written by the maintainer of the package. And what I will show you is the very basic usage of the package, where the user basically enters the metric and uses functions to compute the Christoffel symbols and the relevant curvature tensors. I will assume that you know the very basic. Basically, how to interact with the Maxima interface called wxMaxima, how to enter input in notebooks and how to evaluate, how to assign variables, and how to represent matrices. If you don't, then the wxMaxima help menu has many tutorials and introductory documentation for you to learn all these things. I'm also showing you here a direct link to the online documentation of the ctensor package, which can also be found using the help menu stored in your computer. So you don't really need the internet to access this. Installation of wxMaxima is very easy. For the Ubuntu distribution, all you have to do is to give this command from a terminal, and everything will be installed. If you use a different computer environment and operating system, please visit the wxMaxima site, and you will find instructions. The installation is very easy. I have also made some introductory videos on how to use wxMaxima in these addresses. Unfortunately, they're in Greek, so unless you understand some Greek, maybe they will not be useful for you, but you can try anyway. Maybe you'll learn some Greek in the end, so that will be fun. So the basic usage of the package has a routine that is the same all the time and quite easy. One has to load the package, enter the dimension of the manifold, enter the coordinate system, and basically that means to enter the names of the coordinates to be used in the symbolic expressions, and then enter the metric as a matrix G nu nu. Then there are functions that are used for the computation. In particular, we will see the function symmetric that computes the inverse metric and the determinant of the metric, and does other computations that are necessary under the hood for the following one. So this function must be called before any other computation. And then there are functions like Christoffel that computes the Christoffel symbols, Riemann that computes the Riemann tensor, Ricci that computes the Ricci tensor, C-geodesic that gives us the geodesic equations, L Einstein that gives us the Einstein tensor, and S curvature that gives us the scalar curvature. When those computations are performed, we can use the functions so that they will display the non-trivial results, but the results are stored in variables that are arrays, and we can use them in different expressions and manipulate them according to our needs. In particular, the metric is stored in a two-dimensional array called LG, L for low indices, and the inverse metric is stored in an array called UG, which the U is a mnemonic that the indices are upstairs. Now, the Christoffel symbols are stored in the array MSC. It carries 3 indices, and for the conventions that we are using in the class, we have to be careful because it is the last index of the array that corresponds to the upper index of the Christoffel symbol. The Riemann tensor is stored in the array Riem, has 4 indices, And again, we have to be careful because the package uses a different convention for the definition of the Riemann tensor. So we have to put the last index first in the Riemann tensor when we translate the results, and there is a minus sign that we have to add to the maxima results so that we obtain the results in our conventions. RIC has two indices and gives us the Ricci tensor. There is no difficulty here with translating the results. And L1 has the Einstein tensor. The array geod with an index I gives us the ith geodesic equation, and the scalar variable dim has the dimension of the manifold, and gdet has the determinant of the metric. CT underscore coords is an array that stores the names of the coordinates. So I'm stressing here the conventions with the indices that Maxima, the ctensor package, is using. Be careful here, the minus signs and the rearrangement of the indices. A similar rearrangement and the sign change must be made also for the covariant Riemann tensor. So just to be complete, I'm writing here the expressions for the different arrays that we have just displayed in the previous slide. MCSIJK corresponds to this expression giving the Christoffel symbols, and Riem corresponds to this expression here. For the Ricci tensor and the Einstein tensor, we don't have to worry. The conventions, the results follow the conventions that we use in the class. So let's start with a simple example. So we will start wxMaxima. I'm starting it from the command line here, wxMaxima. Let me also increase the zoom here. And let me show you some information here that you will also find in the notebook that you can download from the site of the class. So here are the basic variables used that I have just shown you in the slides. Here are the functions that you can use and how they're used and how they're called. And here is the routine, how to use the package. So let's see what we have to do. First, we have to load the package using load ctensor. If we have already loaded the package and we want to perform a new calculation, we call init ctensor to clear all the symbols and start anew. Then we set the dimension of the manifold by setting the variable dim and define the metric as a matrix. Then we call cmetric to compute the inverse metric and the determinant, Christoph to compute the Christoffel symbols, Riemann to compute the Riemann tensor, Ricci for the Ricci tensor, Curvature for the scalar curvature, Einstein for the Einstein tensor, geodesic for the geodesic equations, and R invariant for the R square invariant. And that you see here, in order to use R invariant, one has to compute the Riemann tensor with all indices upstairs and all indices downstairs using the functions U Riemann and L Riemann. Now notice the use of some of the functions take as argument false or true. Such functions, when we put true, then they display the non-trivial results of the corresponding tensor. And if we put false, then the computations are done, the results are stored in the variables shown here, but they're not immediately displayed. So let's load the package. So we write the command load ctensor, we put a semicolon, and then we press Shift Enter or the keypad Enter in order to execute the command. So let's start with a very simple example. Let's study the two-dimensional sphere. In order to do that, we define the dimension of the manifold to be equal to 2. Look at this funny notation for assignment for maxima. It has the name of the variable, dim, then a colon, and then the value of the variable. And then all expressions end with a semicolon. Ct coords is another variable that is assigned here. You see the column. And they are assigned to an array that has to be of the same dimension as dim. So we have two coordinates, theta and phi, and when we press Shift Enter, we see that the command is executed and the variables have the values that we have just assigned to them. So let's assign the metric here. So LG must be assigned, that's the metric g mu nu. It is a matrix, so we use the function matrix to define it. And then we put here the rows of the matrix in square brackets separated by a comma here. We can continue the input in several lines to make it more legible. And then when we press Shift Enter, we see the metric in the form of a matrix here. It is diagonal, has a square sine square theta. That's the metric of the sphere in theta phi coordinates. The first function that we must call is symmetric. We don't get anything displayed, but there are a lot of computations that are done under the hood, and in particular, after calling this function, the inverse metric is accessible in the variable UG, and you see it displayed here when I put the name of the variable. And gdet has the determinant of the metric, which is a to the fourth sin square theta. The Christoffel symbols are computed by using the function Christoph. We put here the argument MCS to tell to the function that we want the Christoffel symbols with the final index here to be the Christoffel symbol with one index upstairs. And here is the result. Now just be careful that the last index here is the upper index of gamma mi ni rho. So that is actually the Christoffel symbol gamma 2 1 2. Now this is a Christoffel connection, and it is symmetric with respect to the exchange of the first two indices. So MCS 1 2 2 is the same as MCS 2 1 2. And of course, these are the non-zero Christoffel symbols. Anything that is not displayed is equal to 0. Now these are the non-zero Riemann tensor components in this coordinate system. And this is the covariant Riemann tensor. This one has many symmetries, has only one independent component, the 2, 2, 1, 1. And the Ricci tensor. Is diagonal, has 1, 1 and 2, 2 components. And the curvature scalar for the sphere, it is related to the radius of the sphere by 2 over r squared. Now look at the function cdisplay. You can put here any tensor you like, and it will display it in the form of matrices, taking the two last indices of the tensor and show it here in this two-dimensional output form, and then the first indices here are giving us different matrices. The Ricci tensor is already a matrix, so we can display it this way. Now, of course, you can see all the zero components as well, whereas during the evaluation by the function, only the non-zero components are printed in the output. The geodesic equations on the sphere are those ones. And you can access them through the value stored in the array geod that takes one index, and the index is corresponding to the coordinate name in the order put in CT coords. Let's do something slightly less trivial. Let's do the same computation for the Friedmann metric. We write it in this form shown here, using coordinates t, chi, theta, and phi. And then the metric in a matrix form is also diagonal, and we arrange everything in this order. So before we start the computation, we have to clear all the symbols, so we call init ctensor. And then we repeat the same routine as we did for the sphere. Now the dimension is equal to 4, and the coordinate names are given here, t, chi, theta, and phi. And now the metric is a 4 by 4 matrix. Let's write it a little bit more in this better way here to make it more legible. So you see here, these are the diagonal terms. And notice here that the symbol A is a function of t. And that is simply denoted by putting here A as a function of t. If A was a function of the other components as well, we could put them, we can add them there with a comma. So we confirm that we have entered the input correctly. And that is symmetric. the determinant of the metric is this one. And now let's compute the Christoffel symbols. Here they are. And now we have to take paper and pencil to write them in the conventions that we have defined in the lecture. So here is the result. The index 1 corresponds to t, the index 2 to chi, 3 to theta, and 4 to phi. And notice here that I have to map the indices correctly. So this here, the first line, MCS 122, corresponds to gamma 212, because the last index here is the first index here. So if you want to order them in the way that we have defined, you can just look at the last index here and collect terms according to this value, and make this simple table to use it as you wish. Now let's compute the Riemann tensor. These are the non-zero components of the Riemann tensor, and again here we have to take paper and pencil or our notebooks and translate the results. So here we have to do two things. First, we have to use the last index of the array rim and put it here as the first index in our notation. And then we have to take the result displayed here and flip the sign. So if we want to have correct results, we have to be careful. So you see all the results here, and you see that we have to do some simplifications by hand here to write the more simple expressions than the ones that have been displayed here. This is the Ricci tensor. Has those components here. We don't have to translate anything here. We can just carry over the results to our notebook. Some easy simplifications can be done with the hand here. It's not so hard. And the scalar curvature can be computed using the function S curvature. And here is the result that we write here, which is simplified to this expression here. The Einstein tensor is computed by the function L Einstein, and you see the diagonal components are non-zero, and we can also write them in our notebook. And the geodesic equations are here. Now this is the full output. So you see them displayed, geod 1, geod 2, geod 3, geod 4, and of course we have to solve the equation when each one of them is equal to 0. Now notice the notation here. S is the affine parameter of the geodesic, so TSS is the second derivative of the function t with respect to the affine parameter. but here we have the function at to be differentiated with respect to its argument. Therefore, we have this index t here. So we can pass the results to our notebook and collect terms according to our aesthetic preferences. Now, the computation that is quite tedious to do and can be easily done by Maxima is to compute the r² scalar here. Be careful, if we have not already done it before, we have to call the functions u-Riemann and l-Riemann first. So I did not need to call l-Riemann because I have already done it before, but just for completeness here, I'm showing you the two calls. They both take a false argument, so you see we don't see the non-zero components of the Riemann tensor displayed, and we only see the result for r², which is this expression there. So if you do some simplifications by hand, this is the final expression that you obtain here. So I'm also writing here the definition of the r² scalar. So let's now work another example, the Schwarzschild metric. So let's remember the form of the metric, the coordinates that are used outside the black hole or outside the geometry of a spherically symmetric static star are t, r, theta, and phi, and the metric is diagonal, and in these coordinates it is singular at r equal to 2m, and this distance corresponds to the horizon of the Schwarzschild black hole. So let's compute. We have to start a new computation. So we call init tensor first to initialize the package. Now, since this is a very famous example, this coordinate system is built in the package. So we don't have to define the metric or the dimension or the names of the variables or whatever. We just have to call the function ctcoord_sys, and we put as argument exterior Schwarzschild. So if you look at the documentation of ctensor, you'll see many coordinate systems that are quite common are predefined in the package, and you can define them this way. But we do have to call the symmetric function. So now you see the variables LG are defined. This is the metric, and this is the inverse metric here, and this is the determinant of the metric. Now let's compute the Christoffel symbols. These are the non-zero ones, and again we have to go through the pain to translate the indices to the names of the coordinates, and also arrange the indices using the conventions that we have used in class. So the last index of the array is the upper first index in the Christoffel symbols that we use, and if you do that carefully, this is the result that you will obtain. You can also compare it to the one calculated by Carol in his book. Now let's compute the Riemann tensor. These are the non-zero components here. And again, we have to work a little bit to write them in using our conventions. And here is the result. We have to do two things. First, the last index in the array is the upper first index in our conventions, and we have to take this result and flip the sign so that we have the results as defined in the class. We can also do some simplifications using functions that are built in Maxima, like for example RAT-simp, rational simplification, and we can obtain a much simpler expression for the 1,2 component of Riem here, which you see has this more complicated value when not simplified. For simplifying expressions, you may look also at the menu Simplify. You can do different types of simplifications of expressions here. You just select them with your mouse and then select one of those simplifications to be performed on your expression. Now the Ricci tensor, this is the result, but you know that for the Schwarzschild geometry the Ricci tensor is 0, and it is not obvious from this result, but if you do simplifications carefully, you will see that all the terms cancel and you obtain 0 indeed. You can also simplify using the function RAT-simp, and then you obtain the result that you expect, which is equal to 0. The scalar curvature is 0. The covariant Riemann tensor is this one. You see fewer components because there are more symmetries in the covariant Riemann tensor. And now let's compute the R square scalar, and this is the result here. We can simplify it, and we obtain this expression here. So this is an important computation. You can also find it in Carol's book. It is quite tedious, but its importance is because one sees that there is no singularity at the horizon here. This scalar here is well defined when R is equal to 2m, but there is a true singularity when R is equal to 0. let's look at the geodesic equations. These are the ones. You can work them out. Do some simplifications, and then you will end up with the same geodesic equations as the ones that are computed in Carol's book. So do this exercise with the algebra. The algebra is simple here. Some of the results can be obtained by using simplification functions of maxima. So the third and the fourth equation here can be written by having the second derivative term of the function normalized to 1 using the functions expand. And some other simple simplifications manipulating the trigonometric functions can be done by using the function trig reduce.